Okay, we're gonna do the latest GES 1. It just came out in June. I know you guys are waiting for this and we should go over it. So this might be a bit rough and ready because I'm trying to get this done out quick so you guys can see it as quick as possible. So this will be just June 17th of June 2022, literally just a few days ago. So number 1. Determine the value of x in the following expression if a is equal to -4, b -5, c -3. Really easy on that one. 1a is just a straight plug and play. -4, we have to square that whole thing. X plus b times by c. So I'm going to write it like this. -5 times by -3 is equal to cx. c is -3 times by x. I'm putting everything in brackets because I want to collect all those negatives. Oh, they made everything negative. Oh, that's nice. It's a real pain. Negatives are really difficult to work with. Anyway, -4 squared is going to be +16. -5 times by -3 is going to be +15. And this is going to be a -3x on the end. And then we are going to combine these two x's by adding 3x to both sides. So 16 plus 3 is 19. So 19x plus 15 is equal to 0. Because I added the 3x, it went down to a 0. Let's pop that 15 to the other side. It's really awkward numbers. Just before I continue, I want to check that there's nothing strange about that. Yeah, it looks okay. It just looks awkward. So 19x is equal to -15. We're just transposing it. And then divide both sides to get -15 over 19. That's really ugly. Dividing by a prime number like that is really bad. But okay, cool. So that was part 1a. Let's have a look at part b. Let's see if I can put that over here. Let's grab part b. Part b is simplify the following expressions. Okay, just some basic fractions. Add these guys together, 4/5 and times it by 2.5. Times by 2.5. Okay, there's not much to do with this except from just get it all into sevenths. I could leave this 3 by itself. There's a couple of different ways to do it. So I'm going to pull that 3 out actually. Imagine you had 3 pizzas and I just want to add the slices together, these like bits left over. So it doesn't really matter how I do it. So let's do 3 plus. And then I'm going to make these into equivalent fractions by cross multiplying them. So 5 times by 4 is 20. 7 times by 4 is 28. Over 7 times by 5 is 35. Gonna get a calculator for that. Oh, it's 48 over 35. And the 3 plus that. Yeah, that was kind of useless because I got to pop this up into a whole number anyway. So what's 3 times by 35? Yeah, it's 105. So this can be written as 105 over 35. Yeah, I had to do that for the next part. So I tried to be smart about it. It didn't really work. 48, so 153. 153 over 35. This is the first part in brackets here. So I put it all back into brackets. So it always was. And then this 2.5 is really, that's the same as 5 over 2, isn't it? So let's just drop that down to here. 5 over 2. I wonder, can we multiply these together? Can we simplify them? When we multiply, it's really easy. We don't need the brackets anymore. We can just multiply tops, multiply bottoms. 35 times by 2 is 70. The top bit is going to be... actually, let's just multiply these together. Nice and simple, right? Let's not try and be smart about it. 765. And then, let's see if I can do it on my calculator. So 765 divided by... I'll write it out. 765 divided by 70. My calculator should simplify this for me. It already did into this. And it'll pop it into a real number, into a mixed number if I ask it. If I press shift and then this SD, you can see these little symbols there. It'll give me 10 and 13 14ths. Well, that's probably right. I could run the whole thing from my calculator and check it, but that'll take a little time. So we'll go to the next question. Okay, question 2 is rearrange the following expression to make A the subject. I think we can do that. Question A. That A shouldn't be there. We've got S is equal to UT plus a half AT squared. Let's see if we can rearrange that. Give it a bit more space. There we go. Let's get rid of the ut first of all. So I minus that off from both sides. So we end up with s minus ut is equal to 1/2 at squared. And then we're trying to get a. So I'm looking at this a bit like an onion. I'm looking at this as I'm trying to get the a. So I want to pull these things off. And this is why I moved that ut first of all as the easiest thing to pull off. And then I will slowly work closer and closer and closer to this a. So the next thing to go is the half and the... Let's get rid of the half, which means I got to multiply both sides by 2. It looks like this. There we go. This can just stay like that. It can be 2 s minus ut is equal to at squared. I just cleaned it up a bit. We're looking to make a, so let's get rid of this t squared by dividing by it. So we can just divide by that t squared like that. And we've actually done it. I could rewrite it again in neat if you really wanted. I could even rewrite it the other way around. So we got a is equal to 2 s minus ut over t squared, but I think that's not really necessary. All right, next one is b. Simplify the following expression. Let's rewrite it in my own handwriting because these capital X's are very annoying. I don't like them. 2x over 3 plus 4x over 5. It says simplify the following expression, which means just write it as one big fraction. 2, 3, 5. Well, we can do this in a couple different ways. We can combine these two. I'll try and do it the simplest, I think, the easiest to see for you guys. Let's combine these two as we did like the last one. We're going to cross multiply it. So 3 times by 3 is 9x. 2 times by 2x is 4x. It's definitely negative. And the whole thing, because the negative stays, the whole thing's over 6. 9 minus 4, well, that's a 5 over 5x over 6. Let's make it a bit more obvious. Okay, then the other side, well, this hasn't changed. It just stayed like this. Now it can be applied here at the next step. Let's go 4x over 5. We're going to cross multiply exactly the same process we did a second ago. So we're going to end up with 5 times by 5 is 25x. 6 times by 4 is 24x. 5 times by 6 is 30. We can combine all this together. 25 plus 24. Well, not going to trust my calculations right now. Let's do 49 over 30x. That's really good. This can be simplified into what, 19. So 1 and 19 over 30x. Ugh, I don't like that at all. I preferred this. I think that's good enough. But whatever. You got it both ways. Great. Next question. Okay, so we're gonna do question number 3, which is graphing up this this graph, these points, which I know seems really easy. It's just a bit annoying how they give us the graph and the numbers, and it's very time consuming to have to redraw the graph a few times. So give it some planning before you jump into it, and make sure you get everything nice and evenly spaced, of course. Plot the points. So yeah, I went ahead and prepared this. I had to reshoot this a couple of times because I couldn't get the numbers right. So I just took a screenshot of a set of axes which have the 0.33s on them. I set it up that way, but obviously on the piece of paper you can just write them out this way. Just make sure it goes high enough. I had to check it goes high enough. The maximum is about 2 and the minimum is about -2. So I can get that on here, and then left to right it goes down to -2 on my x-axis. It goes up to 8 on my x-axis. So it looks like I got all those points. Plot the points. Of course, you have to label this out with the x-axis, and this is the y-axis. And then let's plot the points at -2, -0.17. Oh, it's very easy on my graph now. I've got everything labeled up. 0, -1, and then 2, -0.3. Oh, fantastic. You can see the pattern here, so I expect the next one to be here, next one to be here, next one to be here. Let's join them all together. That looks about right. I'm not going over it, extending it, because it doesn't say that. It says plot the points, use an appropriate scale, and draw a best fit line. So this is my best fit line. Just make sure I actually drew them correctly. Yeah, looks good. So there's the first part done. State the general law of the straight line. So general law, this will be part A. Part B is y is equal to mx plus c. This is a general law of a straight line. Determine the equation of a straight line. Yes, of a straight line. This is a general law of a straight line. Determine the equation that best represents the data on your graph. So I got to determine the m and the c for this equation from the graph. Let's see. The c value is the intercept. So that's really easy to see. I can see it from the data right here. It's at -1. So my c will be -1. Then the m is the step length. It's the rise over run. So I can take it anywhere I like. I'm actually going to take it from here because there's a couple of different ways you can calculate it. You can use the equation of y2 minus y1 over x2 minus x1, which is exactly basically what I'm doing. I'm looking at the step length here. This is the change in x direction, which is going from 0 to 2. So this will be the run, and then on the rise goes on top. So the run is 2. How much does it go up by? How much is it going up by? It's going up from, what is that, -1 up until -0.333333. That's 2/3. Ugh, it's going up by 2/3 each time. It's going up by 2/3, and then here I can see a bit clearer. It's going to go up by from -1/3 up to +1/3. So going up by 2/3. I wonder how that simplifies. Now I can do some fraction work on it, but we might as well just do it on the calculator. Get my 2/3 on the calculator, and then divide it by 2. It pops it into 1/3. Oh, I see. Yes, 1/3. So what it's saying is for every one step we take in this direction, we go 1/3 up. One step, 1/3 up. One step, 1/3 up. And we continue this all the way up. This is the gradient or the slope, and that's the m value. So I don't need this formula right now. Just pop it off to the side. What I do need for part C is to say that y is equal to 1/3 x minus 1. It's definitely positive. It's definitely going up. Determine the equation that best represents the data on your graph. This is it. Good. Next question. Okay, question number 4. State Pythagoras' theorem for the triangle in Fig 4. State Pythagoras' theorem for the triangle, not just regular Pythagoras' theorem, because obviously I can write a Pythagoras' theorem. Let's get a bit more space. Okay, so I can write Pythagoras' theorem, which is a squared plus b squared is equal to c squared. But specifically in this case, this is a 10, this is an 11, and this is an unknown. I suppose, well, the 11 is the hypotenuse, isn't it? So we could say 11 squared, and then the 10 squared, and I suppose I could say AC for this bottom there. I don't know if you can see it. That's an A, that's a C. We can say AC squared if you wanted it like that. State Pythagoras' theorem for the triangle shown. Well, I kind of did, I think. Calculate each of the following. So they're actually using the thing. We're going to calculate it for BI, the length of AC. It's already set up, ready to go. So we can say AC is equal to, let's say AC squared is equal to, I'm going to minus the 10 from both sides. So we get 11 squared minus 10 squared. We can actually calculate that right now. So let's do it. 11 squared is 121. 10 squared is 100. So this becomes 121 minus 100 is equal to AC squared, the length of that baseline. 121 minus 100 is just 21, so the length is AC squared is equal to 21, so the length of AC is the square root of 21. I think, normally in mathematics I'd leave it like this, but for engineering, let's write it down as a decimal, as 4.58. 4.58. Is it in centimeters? If we look carefully, the thing is labeled in meters, so we will be using meters on this as well. So 4.58 meters, let's get another couple of digits on there, to 6 meters. Great. Can't complain about that. BII. The angle at C. The angle at C is down here. So I'm going to draw out the triangle so you can see it clearly. We talk about this angle. We know the length of the hypotenuse. Oh, first thing I'm going to do is draw a little guy here. And using him as a reference, and the angle, he's next to the angle, I'm going to label up my sides. So this is my opposite, this is my hypotenuse, and then this is all I need, because we got the hypotenuse is equal to 11, the opposite is equal to 10, and then using SOHCAHTOA, so here's SOHCAHTOA, we are going to find the angle because we've got the opposite and the hypotenuse. So opposite and hypotenuse is a so. So we can say the sine of the angle is equal to the opposite divided by the hypotenuse. And this is now going to be the sine, which we don't know. We'll call it theta for now. The opposite is 10. The hypotenuse is 11. And we're going to have to reverse this to get the angle. So we can say the angle is equal to the inverse sine negative 1 of 10 over 11. Let's type it into the calculator and get the angle out there. So shift sine to get the sine negative 1, 10 divided by 11 equals 65.38. 65.38 degrees. That's it. We got it. Question number 5. This is weird. This is new. Haven't seen much stuff like this before. So, I mean, we'll have a look at it, but I don't expect you to be able to do it straight off the bat because we won't have practiced this a lot because stuff like this doesn't come up very often. It's a bit of a special one. The GES 1 and GES 2 are special like this. They just throw in 1 or 2 spanners in the works, a few curveballs just to... just basically to say that they cover it in the course, or you have to know it for the course, but it doesn't come up that often. It's not even worth learning. It's worth learning a few special examples. There's another one just after this as well. We'll look at number 6, I think. Anyway, define the term for scalene triangle. That's the first question. Scalene is pretty easy. A scalene triangle is a triangle that has 3 sides different from each other with also 3 angles different, of course. I can draw it as a picture actually by labeling each side with these little ticks. So they're showing they're all separate sides. Also the angles, you can label them up by drawing the angles as little arcs. And 1, 2, I suppose opposite 3 would be 3 actually, come to think of it. And opposite 2 would be 2, and opposite 1 would be 1. But let's write it as saying all sides different. All angles different. If you wanted to say it's a 3-sided shape, that would be quite complicated for the triangle part of it, but okay. Only 2 points, but worth getting the 2 points. Now for the next part, which looks hard. Oh, it doesn't look hard, it's just like something we don't usually cover when training for this exam. So it's a bit of a strange setup. It's looking like this. This thing in the key to this is knowing that this angle in the middle is the same. It's called a vertical angle. And it's just like a pair of scissors. Once you open it up on one side, it has the same angle on both sides. And I think we can use that to calculate it. What do we need? We need MBD. Describing your reasoning. MBD. Well, I'm going to start with the left-hand triangle because we know the sides, we know the angles of this. This is 56. This is 78. Now, the internal angles of a triangle have to add up to 180. So I have to describe that when it says describe your reasoning. You have to write this down. I don't know, I don't know how to present it exactly for you guys. So let's just call this, I mean, I could do it in mathematics, but it's getting a bit strict. So I'm just going to write this angle here. And we know that the angles have to add up to 180. So let's do 78 plus 56. I think as long as we're clear about it, it'll be fine. So 78 plus 56, just to show we haven't guessed, basically. 134. So then 180 minus 134 is 46. So we can say this is 46 degrees. Let's actually write a little note on that. So angles in a triangle sum to 180 degrees. I could say the interior, sum of the interior angles sum to 180 degrees, but that's fine. I think that kind of describes what's going on there. Great. So now we're going to do the next side. This also makes, let's make some more space. So this would also make the other side 46 because they're vertical angles. This is also 46 degrees because they're vertical. And to explain my reasoning, I should probably say that. I should probably say vertical angles have the same value. I think I get a point for saying vertical angles because it's a buzzword, keyword. Right, we actually know that one of these other angles. If I go back onto the diagram, it says that it's, what is it? It's 62. So this one up here is 62 degrees. It's given. So of course we can use the same logic here to calculate this last one. Let's say that this angle down here, well, we'll say, my working is very disorganized. I'm sorry about that. I'm trying to do this video quickly. So let's just put it over here. We'll say 46 plus 62. Well, I can do that in my head. I wouldn't recommend it, but hey, I did it. 108. So therefore we can say 180 minus 108 is equal to 72. So this missing angle must be 72 degrees. Describe your reasoning. Yes. Determine the angle MBD. You read this as being from M to B to D. That's it. Looks good. On to the next one. Okay, looks like we got another really hard question. These come up once in a blue moon. But they're kind of set, they're kind of fixed, and the guys I was training this time, people I was training to go through this test, we didn't study this one. We studied the squares and circles, and this is a triangle and a circle. So the good news is that it's always the same. You can just learn it by rote. The bad news is it's pretty difficult. If you've never seen it before, you can't really work it out. It's pretty tricky. But let's try and crack it. Let's try and work it out. So first thing I'm going to do is draw that triangle. It is an equilateral triangle, I think. Determine the area. We've got to find this area up here when the r is equal to 2. So actually drawing this shape allows me to understand what this thing looks like or how it's even built. So let's draw a circle in the middle of it. Try and make it fit a little bit. Okay, great. It has a radius of 2. You see, I think the thing to do here is cut it up into some smaller triangles, maybe. Something like that. Oh yeah, someone did tell me that actually, yes, this does form a right angle. If you have a tangent to a circle from a point, it does form a right angle. That is true. We can use that fact to cut this thing up into smaller shapes. You can see what's going to happen now is that I can keep cutting. I'll do it a different color so it doesn't completely boggle my mind. Here we go, there's another right angle. You can see that all of these triangles are now the same size. So I think this is the key to it right here. That we've got this right angle, this right angle, this right angle here. And they're all the same size as one of those little ones. So all we need to do now is find the area of a right angle, which we can do because that's basic Pythagoras or SOHCAHTOA. We also know the angles, right? We also know this angle down here is 30 degrees because, I'm so sorry, the whole thing is 60 because it must be. It must be. It doesn't say anywhere that's equilateral, but how else can you draw this shape? It must be 60 degrees. I mean, on every single point. It must be symmetrical. It looks symmetrical, but it must be. Otherwise, you wouldn't be able to even build the construction. Most geometric solids like this are perfectly symmetrical, actually, like hexagons and things like that. And because it's 60 on each one, it means that we can say that each one of these is 30, like each half, because we're bisecting it. We're cutting it in half. Okay, great. That means I can pull out this blue triangle now. We can work just with that. So let's grab that blue triangle. Let me move this off to the side so I got a bit more space to work with it. Let's pop it down there. All right. Okay. So let me grab a blue triangle and we'll work just on that blue triangle. I'll keep it the same orientation so it doesn't get too strange. So I'm just copying that triangle out so it looks like this. Okay. Now, the only other bit of information I have about that, apart from this is 30 degrees, is that I know that this is a radius. All of these are radii, all sticking out, and they do tell us the radius is 2 centimeters. So I can use that. I can say that this must be 2 centimeters. Well, this must also be 2 centimeters here. I mean, it's the same triangle. So there we go. We've got this as a right angle. Now I can use SOHCAHTOA to solve it. I'm going to draw a little guy here. This is now my opposite. This, of course, my hypotenuse. And what I need to get the area of this thing is the base. This will be my base here. Oh, so I didn't explain. The reason why I'm doing this is so I can find the whole area of the whole shape because this big triangle is made from 6 small ones. So I find the area for this one, multiply by 6, I get the whole big triangle. Then I can calculate the area of the circle and subtract it. Should be pretty easy to do that. So let's get the area for this thing. The area of this triangle is going to be the base times by the height. I need the base. Let me get the base. This will be my base. Let's call it x. really it's the adjacent, isn't it? So I got the adjacent. I want the adjacent. I've got the opposite. So let's get silly old Harry caused a lot of havoc trolling off Africa. And we've got adjacent, yes. And we've got opposite, yes. So we want to use the TOA. So we're going to write down the actual TOA equation, which is tan of the angle is equal to the opposite over the adjacent. Okay, great. And then we can just plug our values into that. So we got tan of 30 is equal to the opposite, which is 2 over the adjacent, which I'm going to call x. Let's flip the x and the tan. So we get x is equal to, really what I'm doing is I'm multiplying through by x, dividing through by tan 30. But these things come up so often that I'm just going to flip it. I'm not going to bother showing my intermediate working because it's just too clunky. I can, but I'm not going to. Okay, let's get the calculator and type in 2 divided by tan 30. 2 root 3, that's nice. I'm going to probably leave it as 2 root 3. It's just easy for me to type it that way. Let's write down the digits as well. Let's write down 3.464. 3.464. Not so accurate, and by the time I multiply all set up a few times, I want to keep this as accurate as possible. So I'm going to use the non-expanded version. I'm going to use the pure version of it. But this is now my base, so we can write that down. Let's write it up here somewhere. Let's write it as 2 root 3, or let's write it as 3.464. Okay, this is the base, this is the height. So the area of a triangle is going to be base times by height divided by 2. So my base is this, which is 2 root 3. I'm so sorry, I'm just going to use that number because it's easier to type. And then times by the height, which is my 2 divided by 2. Well, I'm not going to even bother messing around with that. Let's just use the number. This is my base, times it by 2, divided by 2. Surprise, surprise, I get the same thing back again. 2 root 3, or 3.464. This is the area of one triangle. There's 6 of them. So now we're going to times it by 6. So the area of one triangle. Let's write down area of 6 triangles. Those are small triangles. This is equal to one big triangle. Might as well annotate it, write a little bit of explanation what we're doing. So this is my area of one triangle. Let's times it by 6. Of course, we're going to get 12 root 3, but now is the time to start putting it into decimals. So let's take this thing, times it by 6, because that's what we have to do here. 12 root 3, let's put it into decimals of 20.784. 20.784 6. What is this in? Centimeters. Okay, great. Let's write it as centimeters squared. So just so we're clear what's going on, let me get my picture. And what we've done is, oh, actually it fits on like that. What we've done is we've calculated the big triangle, the whole thing here, like this big triangle. And now we're going to find the area of the circle. So, and then we're going to subtract the circle from the big triangle. Then I have to remember to divide the whole thing by 3. Mustn't forget to do that because I only want this little bit, not the whole thing. Obviously, I'm going to calculate this whole thing and then I divide it by 3 to get rid of all these. Okay, so this is the big triangle. So part 2 is area of circle. Area of circle. Not so bad. It's just a circle, which is pi r squared. So pi r squared, we already know what r is, it's already 2, so pi times by 2 squared. So let's get some digits on that, some actual numbers. Pi times by 2 squared is 4, so I'm going to risk that. 12.566. 12.566. 37. Let's just write a few more. Now we're going to do the big triangle, so triangle minus circle. And we're going to divide by 3. So I can actually do that right now, couldn't I? Let's just type the numbers in. Yeah, let's do it. So I don't forget it, because last time I forgot it. My students pointed it out. So 20.7846 minus the 12.56637 equals, and then divide by 3 equals 2.73. 2.73941. Yes, centimeters squared. I think that's right. Cool. On to the next one. That's a really difficult one. Okay, so now we're going to move on to section B, which is less pure mathematics and more applied engineering, applied mechanics. So the first part is about a pump is accelerated for 200 RPM to 1000 RPM in 20 seconds. Calculate each of the following: the angular acceleration in radians per second squared. There's a few different ways to do this, and going through this with my students and getting feedback from the course, we see different ways of doing it. So I'm going to be using the way that I use mostly for engineers, because I'm using cut down, simplified versions of it in order to calculate all this angular momentum, angular rotation. I'm going to be using linear, actually, Suvat equations, which are exactly the same. They're very similar. There's just the difference is we don't have to learn two sets of notations. We just use one set of notations. So my equations might look a little bit different, or they might look a little bit different to how you see it in other places. We should be fine. A pump is accelerated from 200 to 1000 in 20 seconds. Angular acceleration in radians per second. So first thing I'm going to do is I want to get this into radians, because revolutions is great, but I always try to get the thing we're working in. I'm meant to be working radians per second. I try to get that to start with. I want to be working in seconds and radians to start with. I don't want to have to fix it at the end. Seconds is good. We've got seconds here, but this is revolutions. So 200 revolutions. I'm actually using a Suvat. So I can write down my Suvat to start with. S-U-V-A-T. Again, we are doing angular, but I'm using linear because the equations are exactly the same. It's just really a perspective thing. And our initial velocity is 200 revolutions per minute. And our final velocity is 1000 revolutions per minute. But I want it to be in radians and seconds. So let's work on those. Let's get 200 revs in 1 minute. Now, I know there's 60 seconds in a minute, so that's quite easy. We can just convert that into 60 seconds. How do I turn revolutions into radians? Well, in a full revolution, there are 2 pi r radians. So we're going to multiply this by 2 pi, because that will create 2 pi radians. All right, so we're just going to multiply it together. It's about 6 radians in a full revolution. So it's going to be about, what, 6 times by 2? It's about 1,200, 1,300 probably. 2 pi times by 200. And it's going to pop it into 1256.637, and this will be radians in 60 seconds. That's great. I don't want 60 seconds. I want in 1 second. So what I can do is just actually divide these just as they are, but the logic behind it is I'm dividing the tops and bottoms by 60, and that turns it into 1 second on the bottom, which is exactly what I need. So let's just divide it by 60. Obviously 65 by 60 is 1, and this on top is going to be 20.94. 20.94395. This is now rads per second. Great. We're going to do the same process for the 1000. I suppose it'll be 5 times as much, because that will just be 5 times as much, but we'll still run it through just in case. It's not normally so easy to see the numbers. So 1000 revs in a minute. Same thing. We're going to turn that into 60 seconds. It's really easy because it's the same process once we've done it once. So 1000 times that by 2 pi. That'll turn it into this many radians per 6283. 6283.1853. Great. This is how many radians we got in 60 seconds. Of course, we don't want in 60 seconds. We want it to be in 1 second, so we divide it by 60 again. Same rationale as before. And we got 104.7. 104.7. Let's get a few more decimals on that. 19197.55. Whatever. This is how many rads per second. Right. So this is now our initial velocity and our final velocity. So we're going to do a Suvat on this using these values. Now we've done the conversions. There's a lot of conversions between units on this. It's basically a lot of your jobs is taking any old units and converting them into the units that we need. Let's give ourselves a little bit of space. Scoot that in a little bit. There we go. So I can get rid of this as my initial and final velocities, and we can replace it with this many radians per second and this many radians per second on the final. Let's zoom out a bit. There we go. Fit it all in. Hopefully you can still seal that. Yeah, it's a bit small, isn't it? Okay, let's keep it here then. So now we're going to use a suvat. I need to go get my suvats. I can't remember my suvats. It's been such a long time. We're going to do S is equal to U plus V over 2 times by T. That's my favorite now, I think. And then we've got S is equal to, oh dear, let's use VUAT, which is V U plus AT. And then I think we've got S is equal to UT plus half AT squared. That should be enough to get us through anything. We probably don't even need like this last one that much. The top one is really important. What are we trying to calculate? The angular acceleration. We want something that gives us acceleration. Oh, we know the time. I didn't put that in. We got time is equal to 20 seconds. So nothing that uses S. So we're going to use this VUAT, the second one over here. And we can just plug the values in, can't we? Let's separate this out. So we're going to use V, which is the 104. So we'll just drag that number down. This is my V. I'm using this one right here, yeah. And then this is equal to my U, which is this number here. Plus, and then AT is going to be the acceleration times by time, which is 20 seconds. The 20 right there. Now we rearrange this, we minus the 20 off both sides, and then we divide by, it's 20.94. So let's just write it out properly. It'll be 104.719755 minus the 20.94395. And then that will get us the A20, and then we're going to divide that whole thing by 20 to get the acceleration by itself. All right, there's my 104 already in there, minus the 20.94395, and divide that by 20. We get 4.1887. 4.18879 rads per second squared. This is the acceleration, the angular acceleration. And like I said, we're just using linear suvats for an angular acceleration. It's absolutely fine. We'll still get the same results. And we don't have to go through all those weird notations of omegas and stuff like that. The final instantaneous linear velocity of a point on the pump impeller perimeter with an effective, what is all this? With an effective diameter of 0.3. So looks like we're going to need some more space, and we're going to go back to the drawing board on this one. Literally, I'm going to draw it. So the final instantaneous linear velocity. So linear velocity means the speed at which something is spinning around. Think of it as we have an object like this. I guess that's a impeller. We have a spinning wheel, and this thing is spinning around. I can spin it around so you can see it. And that blue bit is going to fly off at some point. If you just let go of it and fly off, and it's the velocity at which it would hit you in the face if it did such a thing. Like this, right? So this is what the instantaneous linear velocity is. I'm sure you can all imagine that. Okay, great. Let's see if we can pick this thing apart then and see how hard it's going to hit me in the face, or what speed it will hit me in the face with. The final instantaneous velocity in meters per second. Meters per second. So linear velocity is basically speed, and speed, if you think about it, well, if you know, that's just going to be distance divided by time. I need to know how far it's traveling, and it's traveling on the circumference. It's going round in a big circle. So the distance is the circumference of the circle. And in meters per second, so in 1 second, I suppose, how far is it traveling in 1 second? Yeah, we can do that. The final instantaneous linear velocity, the final velocity, because you remember it has two different velocities. So we're using the final velocity here. This is, let's write down suvat. Don't know if I need a suvat, do I? Nah, it's not accelerating, not changing. It's going to be the velocity, the rotational velocity right now is 1,000 revolutions per minute. And I want to know it in 1 second, because it's going to be the circumference, the distance, over 1 second. Yeah, that's not exactly right. It's how much the circumference we're traveling in 1 second. So let me just get rid of that. We'll come back to that in a second. The velocity right now is 1,000 revolutions per minute. It's going to do 1,000 revolutions every minute. I want to drop this down into revolutions per second. I also want to see how far it's traveling in that time. So like I said, the distance it's traveling is the circumference. Okay, so circumference is going to be 2 pi r, or pi d. I think they gave me pi d, didn't they? Effective diameter. They did. Let's just use pi d. This is my circumference. So it's going to do 1,000 circumferences in a minute. So let's multiply them together. We've got 1,000 times by pi. My diameter is 0.3 meters. Let's crack that through. 1,000 times by 0.3 times by pi. So it's going to travel 942.477 meters. 777,961 meters in a minute. That's great, but I don't want it in a minute. I want it in 1 second. So it's doing it in 60 seconds. So this is my velocity. I'm turning it into linear velocity, I suppose. So we can divide it by 60 the same way as we did before. So the 942.47, etc. Let's round it, divided by 60. So let's just take this number and divide it by 60 because it's 60 seconds in a minute. This now gives me the distance traveled in 1 second. It's now traveling 15.7. It's always traveling at that speed. I can now see that it's traveling at this speed in 1 second because I divided it by 60. Let's just write down what I did. So this is giving me meters per second. So it's traveling at 15.7079 meters per second. Round it properly. Right, let's just check I actually did that correctly. So the final instantaneous velocity on the pump impeller perimeter, which means it's on the outside, which is what we did, with effective diameter of this much. Yeah, it's all good. This is the actual linear velocity at the end of the day. This is how fast it's going to fly off and hit you in the face if it did such a thing. Ooh, okay, next question. Okay, let's look at number 8. A casting of mass of 26 kg has a horizontal force applied to it and causes acceleration on a frictionless plane. Frictionless plane, it's all horizontal, so it's pretty easy. Let's draw a picture of it first of all. So we're talking about a body, it's basically a box, and it's 26 kg, and then we're going to be pushing this thing with 180 newtons for the force. Great. It's really easy because it's frictionless. Well, that's about it, isn't it? So, nice. Okay, cool. We're going to be using F equals ma for this thing with acceleration of the body. This is it. There's no friction. There's nothing. It's so easy. So we can fit it onto one page. It's F is equal to ma. The force applied is 180 newtons. The mass of the object is 26. The acceleration is a. So we divide through by 26. We'll get A. Easy. Normally we have to calculate friction, all sorts of stuff. That is crazy. We don't even have to do anything on this. 180 divided by 26. It makes a nice change from the other questions. 6.923. That is pretty fast. 6.923. This is acceleration, so it's meters per second squared. Horizontal force applied to it in a frictionless horizontal plane. I can't believe it. I can't believe how easy this one is in comparison to the rest of them. So they gave us some really hard questions to start with, and then these are much easier. Okay, let's have a look at B. The distance the body will travel from rest in 8 seconds. So it's a suvat. Let's apply a suvat. Again, we got to get our suvat equations, but let's have a look. We want to know the distance. This is actually what we're looking for. We know the time is 8 seconds. It says from rest, so this is a 0. And then we know the acceleration of the body is, we just calculated, is 6.923. Let's get some equations. So U, let's use VUAT, VU plus AT. That's no good. S is equal to U plus V divided by 2 times by t, this is no good. S is equal to ut plus half at squared. That's the one we're looking for. We're looking for s, so we're going to plug it in as x. U is going to be 0. And then a half a, which is 8. No, it's not. It's 6.923, 8 squared. Let's get a calculator and just plug it in. This is such an easy question. I'm going to use 0.5 instead of a half, times by 6.923, and then times that by 8 squared. 221. 221.536 meters, or thereabouts. That's the distance the body will travel from rest in 8 seconds. Well, easy. Next one. Okay, let's look at number 9. This is going to be quite a long one because it's a beam, it's got a lot of loads, and it's A and B reaction forces. Looks fine. Looks like a standard setup. 10 points, worth doing. We've got a nice little table that will make this a lot quicker, a lot easier. We just need to draw a picture of the diagram, but I've already got a picture, so I don't really need to draw it anymore. So you obviously need to copy it down. Oh, just one more thing is that the mass of the beam is not on there. And I would like to include that. I'm going to squeeze it in here for speed. The mass of the beam we're taken exactly from the center, and it's going to be at 800 kilograms. So 800 kg. And because the beam is 6 and 1 long, it's 7 meters long. The distance from the pivot, which is what I want from A, is going to be it's going to be 3.5 meters. Because 6 plus 1 is 7. 7 divided by 2 is 3.5. That's all the information we need to get this thing started. So let's go. Let's go for it. We're going to be using a table. And my table looks like this. We start with the name of each of these loads. The force. Nope. The weight. Nope. We're going to call it mass. It's better to say mass. And then we got the force created by that mass. The distance from the pivot. And then also the moments. Let's add a few more details into this. So the name, let's call this weight 1. We'll call this weight 2, weight 3. We can call this weight 4, and we'll call this the beam. So we're going to have those. We're going to have weight 1, weight 2, weight 3, weight 4, and the beam. We also need one more thing because we're taking, I got to zoom out a bit on this to fit it all in. It's getting a bit small, but we need to, let's see if I can make it a little bit bigger. We need to get this to fit on the page. 1 second. Much better. Okay, and I didn't write down anything like this, but I'm going to be taking moments. I'm taking moments about A, which basically means a pivot at A. So all my relations, all my forces are pivoting about A right here. Right. So, which basically means if I was imagining this, I would be lifting at this point here, and we're seeing how much force is required to lift it. That's what taking moments about A means. We need a few more bits of information, a few more explanations about what we're doing. Let's also say that the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. This is our rationale for the calculations we're doing. And we need to explain it to get the points in the exam. We need to be clear about what we're doing. Also, I can just say the sum of the downwards forces should be equal to the sum of the upwards forces. Because everything pushing down should be equal to everything pushing up. This thing is not moving. It's in equilibrium. It's not jumping around. It's not spinning or anything like that. Okay, there's our rationale. There's our explanations. Let's go ahead and fill in this table. We got the names of the forces on these guys here. Right. Then we got, some of these have got masses. Some of them go directly into forces. I'm so sorry. Let me space this out a little bit more so we can see clearly what's going on. The masses will be done in kilograms. So we better write that. Let's write this down to be clear. Kilograms. The forces will be done in newtons. The distances will be done in meters. The moments will be done in Newton meters. And then we've actually got direction of force, which I normally just write as a clockwise, anti-clockwise, but we could just write direction of rotation. That says rotation. And it's going to be anti-clockwise or it's going to be clockwise. Great. Let me just drag that out, make it look like a table. And we can start filling this thing in. This is going to save us a lot of hassle. Okay, so the mass of the weights, we don't have the masses. We just have the forces directly on there. That's okay. We do have the beam though. The beam, oh, I forgot one thing. Let's put the beam on there. It's 800 kg. I forgot one thing, and this is the reaction force at B. Because this guy lifting it is going to be counterbalancing all of these weights pushing down. The pivot is just pivoting. Right. So we've got 800 kilograms. In order, the forces are done in kilonewtons, so they're pretty big. I suppose I can keep it in kilonewtons. What are we going to do here? I was going to get over massive numbers. Let's turn it into kilonewtons. So this is going to be 30. Otherwise, it's going to be really clunky with 30,000, 20,000, 35,000. It's just going to be way too big. Which also means my moments now going to be in kilonewton moments. And then the last one here is 40. I need to calculate this, so I can calculate it by multiplying by 9.81 because obviously we're under gravity. So we've got 0.8 tons. Because we have to turn it into kilonewtons. So I could do the calculation as 800 kilograms times by 9.81. This is kilograms and gravity. It produces this many newtons. Oh, that's pretty easy. 7.848. 848. That's great. We got it in kilonewtons. It wasn't that hard. No messing around. And then the reaction force, I don't know what it's going to be, but I'm going to label it as X. This is what we're calculating. We just need to make all of these a little bit longer so it looks like a table. Okay, looking good. Now the distance from the pivot, this is actually one of the hardest things to calculate. Let's see if we can plug them all in. That weight 1 is 1.5. Luckily they've given us everything from point A, which is really useful. 1.5, this is 3, this is 4, and then this is the whole thing. So that's, I think that's a 6 and this is a 1. So you probably can't see that there, but it's a 6 and a 1, so the whole thing's going to be 7. And then the beam, at the actual center of the beam, I worked that out at the beginning of the exercise, that's 3.5. And then the reaction force where this guy is standing is at 6. Wow, okay. Let's get all these into moments. 30 times by 1.5 is 45. 20 times by 3 is 60. 4 times by this, I think, is 140. 35 times by 4 is 140. 140. 7 times by 40 is 280. This is an awkward number right here. Let's see if we can calculate it as being... Let's see if we can calculate this as being 7.848 times by 3.5. Let's see. It's 27.468. 27.468. And this last one's going to be 6x. Okay, looks like we're good to go. Now we just got to look at what these rotational forces are. If they're going to be like rotating down or rotating clockwise or anti-clockwise. Remember we're pivoting about A, so all of this is going in this direction. If it was free to move, it would just move in this direction by itself. So all of these forces are going to be clockwise. So clockwise, 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 clockwise. The beam is clockwise. The only thing, poor guy, that's anti-clockwise is that guy there, which is the reaction force, so it's anti-clockwise. Let's clean this back up again. Okay, now comes our rationale. The sum of the anti-clockwise moments is equal to the clockwise moments. So I'm going to drag this down because we need to get to work on this. The anti-clockwise moments is all of these guys here. This is all anti-clockwise. And then the sum of the clockwise, well, actually I said it backwards. The anti-clockwise moments is 6x. That's that one. And then all of this added together will be the sum of the anti-clockwise. So I could write it down, but it's going to take up a lot of space. Let's write it down. 45 plus 60 plus 140 plus 280 plus 27.468. 45 plus 60 plus 140 plus 280 plus 27.468. 4, 6, 8. Add them all up. I got 552.468. Now we're trying to calculate x. Now x is actually the force in kilonewtons of the reaction force at B, which is actually what we need. So x is equal to, we take the whole thing divided by 6. Divide by 6. 92.078 kilonewtons. This is the reaction force at B. Let's just check what we need. Calculate each of the reaction forces at A and B. So we've got B. Now we have to calculate A. And a really nice shortcut is that we can just use this rationale here. Here we go. The sum of the downwards forces must be equal to the sum of the upwards forces. So we just found the reaction force at B. So we can actually say that the sum of the downwards forces, that's everything pushing down. And we got them all in our diagram up here, in our table, sorry. Here they are. I'm going to copy them out. These are the forces. Drag them down. Okay, sum of downwards forces. So it's the 30, the 20, the 35, the 40, and the 7.8. These are all the downwards forces. Let's pop them over there, put a plus in between them. Okay, now the sum of the upwards forces is literally the reaction force at A plus the reaction force at B. And we just found the reaction force at B. It was this. So I'm going to go ahead and remove that and pop it in here. Right, this whole thing is, everything's in kilonewtons, so we're all good to go. We just need to add up all these, which are now forces. It's not the same as the newtons. It's not the same as the moments up there. That moments was a little bit different, right? These are just downwards forces. So we have to do the calculation again. So it's 30, it's different calculation. Plus 20, plus 35, plus 40, plus 7.848. 132.848. 132.848. That's an 8. Now we've got the reaction force at A, and we're going to minus off this 92, of course, to find the reaction force of A. So let's take our number, and we'll just minus it off. Minus the 92.078. Great. 40.77. 40.77 must be the reaction force at A. So we've got the reaction force at A, we've got the reaction force at B. I didn't say this is in kilonewtons. I did now. So good. Check the question. I think we did it all. On to the next one. Okay, question 10. This looks like quite an easy one. They're all 2 pointers. They're all just definitions. Now, definitions is not really my strong point. It's quite difficult to get them out in a video. It takes quite a lot of wording and writing it. Everyone's going to write it a little bit differently. Make sure you understand it. Make sure you can write it out. But I'll give you a couple. I can write down the equations for sure. So, for a simple machine, define the term force ratio. Force ratio. And the other one's velocity ratio. I need to look at everything together. Velocity ratio. So I don't get mixed up between them, because these have different names. Like, I would normally use my formula, which is EFM. This is efficiency is the force ratio over movement ratio. So velocity ratio is also called movement ratio. And that's basically the distance you're traveling and versus the distance that the object is traveling. Now the force ratio is going to be also called mechanical advantage, mech advantage. And it's the amount of force you're applying versus how much force we're lifting. I say versus, but it's not the best way to say it. Can we say it a little bit better? The force ratio then is, I know the smaller number always goes on the bottom and the bigger number always goes on the top. So the way that's how I remember it. This mechanical advantage, let's see if I can fit it in like this. So is the force being lifted? And I don't know if I should call it applied force, but we'll just write it in simple English. Force lifted. It's not always lifted. This is the problem. Technically, this is not always true, because sometimes we're lifting things, sometimes we're pushing or cracking or breaking things. The force lifted over the force applied force. That's the force I'm putting into it. And it would normally always be given as just like a number, and this number is the number of times I can lift. So if I put in 10 newtons and it has a force ratio of 4, it means I can lift a force of 40 newtons from that 10 newtons put into it. So again, I can say that in the explanation. Okay, this is the force ratio. That's part A. Like I said, you need to add a sentence in here, but I'm not going to do it right now. I'm just going to talk you through it. I'm doing it orally. You need to write it out because obviously the marker can't hear you talking, can't hear your explanation. You need to write all this stuff down. So the velocity ratio is the same as movement ratio. It's the distance you travel versus the distance the load travels. The distance I travel, and I always think of it in terms of me pushing a lever, traveling around in pushing a wheel around and lifting up an object. So the distance I travel versus the distance, or over the distance the object, the distance lifted. How can I say this? Distance the object travels. And they're flipped. They're really, really flipped, because like this is the force applied, that's me pushing, and now I'm traveling on top. So I have to remember it, like you always put the big number on top and the small number on the bottom, because you're always going to be lifting, for example, like 100 newtons by applying like 10 newtons of force. And you're always going to be like, the distance I travel is going to be, I'm going to have to travel like 10 meters to lift something like 1 meter. So they're completely flipped. Okay, this is the force ratio and the velocity ratio. Now we got to look at state the expression for mechanical efficiency of a simple machine in terms of force ratio and velocity ratio. Well, this is just efficiency, isn't it? So we can write that, no problem. Let's zoom out a bit, get a bit more space. So efficiency is equal to the force ratio, is EFM. So it's the force ratio divided by the velocity ratio or movement ratio. We'll use the same language, velocity ratio. This is the formula. I just want to say one more thing about this, which is, I mean, that's all it is. It comes out, it's always, you always know that this is the right way around, because you can't have a greater than, like this, it comes out as a decimal. So this could be equal to like 0.89, for example. You can multiply it by 100 to turn it into a percentage, but you can never have more than 100% efficiency on a machine. You can't even have a 100% efficient machine. As a laws of physics, it's a law of physics that you always have less than 100%. So that's how you know you got it right way around, is that you should have a number less than 1. Like when you calculate this, you get something like 0. Like I said, 78 or something like this. Or if I times it by 100, I'll get the 78% efficiency. I want to say one more thing about the mechanical advantage, or the velocity ratio. Yeah, this thing here, the force ratio, is this actually has to come empirically. You actually have to measure it from the machine. The velocity ratio is a theoretical calculation. You can say, oh, I'm moving 10 meters, the thing moves 1 meter, so I can work out my leverage on that. But the force ratio is literally actually measured from the machine itself. It has to come from that. This is why we get like a 78%. It's always this actual versus theoretical. And the theoretical, yeah, maybe I said that backwards. Well, I'll stop talking then. Like I said, definition is not the best. State why mechanical efficiency is always less than 100. Well, I did say it because you can't have more than 100% efficient. You'd be like pushing something, it would just give you energy. It's like having a perpetual motion machine. It's a law of physics. I think that'll do. All right, on to the next one. Okay, number 11. Describe what is meant by shear stress. So, shear stress is the breaking stress of an object or material. It's exactly what you use for cutting when you use a pair of scissors. You shear the paper in half. And I guess we could say it's measured in Newton meters, newtons. It's a pressure, right? Stress, which is what we're going to use in a second for the rest of it, is force over area. And so it'll be in newtons per meter squared. And it's the amount of force or amount of pressure required to completely break the material, to completely cut it, or to, at failure, I suppose, it's going to fail. And you can see it on one of those stress strain graphs that goes up like this. And is at this failure point up here because we're actually cutting the material, actually breaking the material. Okay. So that's part A. I need to give it, like I said, a couple of sentences to explain that. One sentence to explain it will be fine. Now we get to the actual work. A hydraulic press is used to punch a rivet holes in a steel plate, in metal plate. Okay, so we got a steel plate. We're going to be punching holes in it. So let's draw a quick diagram of it. Looks a bit like this. They're usually quite thick steel plates in these questions. And we're punching a hole in it. And this diagram is kind of important so I can see what's going on. So I can get a really clear picture. There we go. Looking something a bit like this. And it's going to punch out around. It's going to punch out a little disc. Right? And that disc is important because of how it's stuck in there. Like the surface area of the curved surface area is what's really important in this question because that's what we're breaking. We're breaking all of this. You imagine all those atoms and atoms really just sticking this thing together. This is what we got to break. We got to break that electromagnetic force that's sticking this whole thing together. Okay. So a hydraulic press is used to punch a rivet holes in a metal plate. The plate is 5 mil thick. 5 mil. Not that bad. Normally they're like 2.5 centimeters, like an inch thick. And the holes required should have a diameter of 10 mil. Pretty small. Again, normally about an inch. A force of 40 newtons is required to punch the hole. Determine the shear stress at failure of the metal plate. Let's see. Stress. So we want to bring it to its failure. So we got stress is equal to the force. Well, they've given us the force. They said it's 40 kilonewtons. I can drop it into regular newtons. I don't think it makes much difference. And then we need to calculate the area of this thing. So the area, what is the area of that? That is the curved surface area around the outside of that cylinder. So if I draw a quick cylinder, a net of a cylinder, the surface area is quite difficult to remember and get your head around as well. So it's a long, thin strip in this case. It's going to look a bit like this. I'm drawing a quick diagram so you guys can see it. It's this part here that we need to calculate. Because like I said, that's the bit that's sticking it in there. And the length of this is the circumference of the circle, which is pi d. And the height of it is the thickness of the plate, which I just call h. So the area of this is pi d h. Pi d is going to be diameter, and they said it's 10 mil. So let's put it in as 10. The height of it is 5, so let's put it in as 5. Let's calculate that. It'll be 50 pi. 10 times by 5 times by pi. 50 pi. And that creates 157. So it's 157.0796 millimeters squared. That's great. We can put this into the area we have here. And this will tell us the stress. This is all we got to do. This is all we got to do the whole question. That's really nice. So let's have a go. Let's put stress is equal to 40,000 newtons and 157.0796 millimeters squared. We're just going to remember the units. We've got to state this at the end. So 40, 1, 2, 3, divided by the 157. I've already got it in my calculator as an answer. Just type it in. 254. 254.64 newtons per millimeter squared. This is the ultimate shear stress. Determine the shear stress at failure of the metal plate. This is it. We broke it. By applying this force over that little bit of area, number of newtons per millimeter squared, that's the stress. Okay, question 12, last one. State the difference in static and dynamic friction. Well, static friction is when you're pushing an object that's not moving. Dynamic friction is when you're pushing an object that is moving. Static friction tends to be greater than dynamic friction. You can think of this as when you're pushing an object, it takes a while to get it moving. But once it's moving, it's a bit easier to move. But getting the thing moving is a little bit more. It tends to stick to the ground a little bit. This is static friction. Okay, so let's have a look at part B. Let's make it a little bit bigger so we can see it. A container has a mass of 400 kg. So let's draw a diagram of this. 400 kg. And is pulled along a horizontal plane by a cable. Horizontal plane. Let's put that in like this. Okay, the cable makes an angle of 10 degrees above the horizontal and has a tension of this many kilonewtons. So let's draw the cable on. I'm going to move my picture a little bit so it fits a bit better. Okay, 10 degrees. So I've got big fat cables on here, but this is 10 degrees. I'm accentuating a little bit so we can see it. Above the hand has a tension of 1,800 newtons when it's pulling at a constant speed. Determine the coefficient of friction in the container. So we've got a little bit of work to do on this. We've got to look at the vertical and the horizontal motion of forces acting upon this object. So we're going to do that. We're going to look at each one. Let's see if we can annotate our work, and we will write horizontal, vertical, and then like final. We're doing like paragraphs going off to the side. So I need some formulas for this. I'm going to be using a bit of SOHCAHTOA to start with. So what I want to do first is, I don't know, look at the forces pushing this thing down. So that'll be the vertical. And then I also want to look at the horizontal, which is the forces pushing it along. Horizontal. Great. And we're going to use SOHCAHTOA to break this apart to get those two forces out of it. So can I do that without using up all my space? I think so. Here, I'll just copy this force diagram, this force triangle off to the side. This triangle is this blue one up here. Excuse me. Right, okay, so this is 10 degrees and this is 1,800 newtons. And we can use SOHCAHTOA to get these two parts. Let's call this the Y. Let's call this X because the Y is vertical, X is horizontal. In order to get the X, we're going to use K, because I've got the adjacent, I've got the hypotenuse. So I can say cosine of 10 is equal to the adjacent over the hypotenuse. And let's multiply up to the other side to get my X by itself. Sorry, I just realized that I kind of did that backwards. I'm doing the horizontal first, but it's the first one that popped into my mind. Let's calculate that as being 1800 times by cosine of 10. Okay, 1772. 1772. 0.65 newtons. Let's write that down on the diagram, make it a bright color. 1772.65 newtons, pushing this thing along or pulling this thing along. That's great. Now we need to do the vertical. The vertical is exactly the same, but it's just going to be cosine. I mean, sine. We already did cosine. Let me move this down here so I got a bit more space to work in. So we're going to say, we're going to use the SO from SOHCAHTOA because I want the opposite and I've got the hypotenuse. So we can say, let's get another color so it stands out. So we're going to have sine of 10 is equal to the vertical over the hypotenuse. Let's rearrange that into 1800 sine 10 is equal to y. Very similar. It's always the same kind of setup, which is really nice. I can even just backspace in my calculator, type it in there. So 1800 sine 10. That's the calculation we're going for. 312.566. 312.5667 newtons. Now this is pushing it, or pulling it up, not pushing it down. It's pulling it up. So on the diagram, I can push it up here. This is really good because it's actually going against that force pushing it down, which is going to reduce the amount of friction it feels. So it's going to make it easier to push. So that's really good. So 312.5667. Okay. Where are we now? We've got the vertical, we've got some of the vertical forces, we've got the pulling up, and then we've got to get the pushing down from the actual container itself. What can I do this thing? I can move it out someplace. I got to make a bit more space. I always need more space. Does that fit still? Can you still see it? I think that's okay. All right, let me just scoot this across over here. Get the vertical. Okay, just get organized, looking good. So now we need to talk about how much the box itself is pushing down on the ground with, because the rope is pulling it up by this much. This is up, but now the box itself is, let's write that as box, is 400 under gravity is 9.81 F equals ma or mg. 400 times by 9.81 is 3924 newtons down. So it's pushing this many newtons downwards, and of course it's going to counteract with this, so we can get the net force, the net or the overall force in the vertical direction. Net force is going to be this much down minus the 3112, the 312.5667, pushing it back up or pulling it back up. We got 3,611.433 newtons down. This is pushing it down. And this is what's going to create that friction force. We don't have the friction just yet. We got to look at that. But this is what's going to contribute to it, because friction is fun. It's is F-U or mu N. And this is the N. This is the normal force pushing it down here. And we can calculate how much friction force there is now from the horizontal. Actually, we already have it because this is what's pushing it forwards. So let's do this off to the side. Let's make friction up here. Let's take friction. Let's give it a little subtitle. Make it as clear as we can. We're calculating friction now. Friction. And we got the pushing force must be equal to the resisting force. Otherwise, it wouldn't be moving at a constant velocity. Pretty sure in the question it says it's traveling at a constant speed. If it was traveling at if it was getting more push than it was pushing it backwards, it'd be accelerating, but it's not accelerating. So it must be exactly the same push as the resisting force. The friction force must be equal to the push. So the push is this much. 1772.65 is pushing it forwards. Mu, we don't know, we're calculating. And then the thing contributing towards the downwards force is this 3,611. We'll just pop it in there. All right, now we can calculate mu, which is what we're after. So we do 772.65 divided by 3611.43333 is equal to mu. Pop it through the calculator. We got 1772.65. Nope, 1772.65 divided by 3611.4333. Hit it and we get 0.49. Not bad. 0.49. It's a bit high, but hey, what are you going to do? 0.8 is our coefficient of friction for that situation. And it looks like we finished the whole test. So that's really good. Thanks very much.